This video will discuss the solution to question 38. Figure 6 shows a dual slope ADC. First, for a fixed number of cycles N1, the input signal Vin is integrated. After that, for a variable number of cycles N2 minus N1, the negative Vref voltage is integrated. Assume that N1 is 1024, f clock is a megahertz, and Vref is 2 volts. With the given information and assuming that N2 is 1088, what is the value of Vin? To find the value of Vin that yields us the given N2, it helps to first derive the transfer equation of this circuit. So, what input gives what output? We can start doing this by looking at the behavior of the output voltage of the integrator. We know that in the first phase we integrate the input voltage for N1 clock cycles at a frequency of f clock. We can describe this voltage with an integral with a certain factor 1 over tau, which is just a constant factor, multiplied by the integral from 0 to t of Vin. Since Vin is a DC voltage, this integral can simply be rewritten as a multiplication with time. If we now want to find the voltage after N1 clock cycles, or the voltage at the peak, we can simply evaluate the Vin function at N1 over Fs, or in other words, N1 times the clock period. This gives us 1 over tau, Vin N1, times 1 over f clock, and we will also denote this as V peak in the following equations. We know that in the second phase we will start from V peak and then integrate the negative reference voltage from N1 clock cycles to N2 clock cycles. Since we know the behavior of the integrator, we can write this as V peak plus 1 over tau times the integral from N1 over f clock, so that's the time at which we register the peak, to t, and we integrate the value of negative Vref. Now again, since Vref is a constant voltage, we can rewrite this integral as a multiplication. So we now get 1 over tau f clock times N1 Vin, that is the peak voltage, minus 1 over tau Vref times t minus N1 f clock. We can now use some information from the diagram. We know that the integrator voltage at N2 over f clock is 0, so we can simply equate this expression to 0 and then rewrite it. Notice that both the left-hand side and the right-hand side contain the same factor, 1 over tau f clock. Tau is a constant that is typically determined by the component values inside the integrator, and f clock is the clock frequency. Apparently, the transfer of this circuit does not depend in any way on the integrator implementation or on the clock frequency. This leaves us with the final transfer function of N1 Vin being equal to Vref times N2 minus N1. And we can now fill in the given parameters for N1, N2 and Vref to obtain an input voltage of 0.125 volts with the equation above.